Welcome! We'll be looking at one of the aspects when we need to consider when choosing a third-party library that will be used in our code. So we'll be importing a library and taking full responsibility for its settings. Beware of the defaults. So some libraries and frameworks, like for example Spring, favor convention over configuration. Such a pattern allows potential users to start using a specific library right away without any necessary configuration. It trades off explicit settings for the simplicity of UX. As long as an engineer is aware of this trade-off and its limitations, there is no real danger. The prototyping and experimentation phase is a lot easier and faster when using software components that do not require a substantial configuration upfront. Those frameworks are built using best practices and patterns, and they should be good enough for you as long as you are aware of the drawbacks and problems. The fact that the majority of all configuration is based on convention has some drawbacks as well. When you are using a third-party library, it's tempting not to dig deeper into all its configuration options. If you leave the defaults unset, we rely on the configuration that is shipped within a library. The values that become defaults are usually picked in a sane way based on some research. However, even if the defaults are a good fit in most contexts, they may not be good enough for your use case. Let's consider a simple scenario when we want to use a third-party library that is responsible for HTTP calls. We'll pick the OK HTTP library for the demonstration purpose. We want to query the data that is available under data endpoint of the service. For the testing purpose, we'll mock this HTTP endpoint using WireMock library. We will stub the data endpoint that returns the OK status code and some entities body data. It's important to note that our WireMock will start on a dedicated port. Here it is 9999, but you can pick any other port or you can do it in a random way. Also, we need to save the location of the URL to the host variable that will be used later in our tests and code. Finally, we are mocking our data endpoint that will return 200 with some data within the body. We have a second one, but it's not important right now. We'll get back to it a little bit later. After the test will finish, we need to stop the WireMock server. So let's take a look at the first use case, first test. The OK client logic for querying the service and getting the response is very straightforward. We build the URL based on the host variable. Next, we are building the OK HTTP client using the builder and executing the call. So here is the call execute. Finally, we are asserting that the response is 200 and the content matches the content stubbed by WireMock. So let's start the test and see if it passes. Our test is green, so it means that we were able to query the service successfully and get the proper response. Please note that HTTP client is created as a builder, but no explicit setting is specified. The code looks very simple and it's fast to start development using it. Unfortunately, it shouldn't be used in production in this specific form. Remember that once you import the third-party library to your code base, you need to start treating it as your own code. And we'll focus on defaults, so let's see which settings may be problematic. When analyzing the third-party library config, you need to understand the main configuration settings. In the context of every HTTP client, timeouts play one of the crucial roles. They will impact the performance and SLA of your service. For example, if your service SLA is 100 milliseconds and you are executing the code to other services to fulfill this request, the other call must be completed faster than your service SLA. It is crucial if you want to keep your SLA. The high timeouts are also very dangerous in the microservices architecture. In this architecture, to deliver business functionality, there is often a need to do multiple network calls. For example, one microservice may need to call multiple other microservices. Some of those others may need to contact the following microservices and so on. In such a scenario, when one of the services hangs on the request processing, it might cause the cascading failure of other services that are calling it. The higher the timeout is, the longer it may take to process a single request, and there is a higher probability of cascading failure. Such a failure may be worse than breaking the SLA because it involves a risk that the system will crash and stop working. So let's see how our client will behave if we query an endpoint that takes a long time to execute. We will test it for 5 seconds, 5000 milliseconds. We can simulate this scenario in WireMock by using with fixed delay method. So here is the method that we are calling on this stub. We are calling this new endpoint slow data URL. We will execute this query using the same logic, but we will measure the time it takes to execute the HTTP request. But this time we are executing request to slow data endpoint. So we are starting our timer before the call execute, and after that we are calculating the total time. At the end, we are validating using assert that the total time that it took to execute was greater than or equal to 5000 milliseconds. Why? Because the slow endpoint that returns this with fixed delay will take as much time to execute as this. Then you are verifying that it was 200 and some data. So everything should work, but it should take 5 seconds to execute. Let's start and see. We are waiting a couple of seconds, as you can see. Yeah, and after some time, it finishes. So it means that request took more than 5 seconds or equal to it. It is happening because the WireMock HTTP server introduced that kind of delay. If our code that needs to fulfill the request within 100 milliseconds calls this endpoint, it will cause enough slowness to break the SLA of our application. Instead of seeing a response in 100 milliseconds, whether the response is success or failure, our clients will be blocked on wait for 5000 milliseconds. It also means that the thread that is executing this request may be blocked for that long time. One thread that is supposed to execute 50 requests, so 5000 times 100 milliseconds, will be blocked. Thus, this thread won't serve any other request for that amount of time, impacting the overall performance of our service. This problem may not appear if one of the threads is waiting too long. However, we'll start noticing performance problems if all or the majority of allocated threads are blocked for that long. It turns out the default timeouts settings cause this situation. Our clients should fail the request if we need to wait for more than our service's SLA, in that case 100 milliseconds. If the request is failed, the client can retry it instead of waiting for the 5000 milliseconds for any response. If you look at the read timeout of the OK HTTP library, you will notice that the read timeout is set to 10 seconds by default. It means that every HTTP request may block the caller execution for up to 10 seconds. Such situation is far from ideal. In a real-world system, you should configure the timeouts according to your SLA. We are assuming that our code must execute the call to a slow data endpoint with up to 100 milliseconds. We are also assuming that the service that we are calling has a defined SLA of 99 percentile equal to this 100 milliseconds. It means that 99 out of 100 requests will be executed within 100 milliseconds. There could be some outliers that took longer to execute. You are simulating such an outlier that takes 5000 milliseconds to execute. We will execute the HTTP request once again, but this time let's provide an explicit setting for the read timeout instead of relying on the default. Please note the read timeout method that is used to specify that timeout. We are setting the read timeout to 100 milliseconds, the same amount that our SLA defines. At the end, we are verifying that the request will fail fast, so it will time out in less than 5000 milliseconds. Our timeout is slower, it should fail fast. So let's run it and see how does it behave. We get the result almost immediately. Calling the execute method is triggering the actual HTTP request. The request will fail after around 100 milliseconds because this is the new timeout that we specified. After this time, the exception is propagated to the caller. The exception is socket timeout exception, denoting that we get the timeout. Therefore, the SLA of our service is not impacted. Next, the request can be retried if it's idempotent, or the info about the failure can be saved. Most importantly, the HTTP service's slow response will not block the thread for a long time. Thus, it will not impact the performance of our service. So when you are importing a third-party library, you should be aware of its settings and parameters. Implicit settings can be suitable for prototyping, but explicit and well-tuned settings for your context are must-have for production systems.